For this problem, we need to find the Fourier series coefficients of the sawtooth wave. It's modeled by this equation, 1 over t times the integral over 1 period of x of t, which is just the periodic signal, in this case the sawtooth wave, times e to the negative j 2 pi n t over big T, all with respect to time, where t is the period of this periodic signal. So we see this first sawtooth starts at t equals 0 and ends at t equals 3, and the next one begins at t equals 3. So the period is going to be 3 seconds. Next, we need to determine the bounds of integration, or the interval that we're going to integrate over. We can pick any 3-second interval. For example, negative 3 to 0, or negative 2 to 1, or really any 3-second interval. So the easiest one is going to be 0 to 3, because that gives us one sawtooth pattern, and it also gives us a bounds of integration of 0. Next, we need to determine what x of t actually is during the interval t equals 0 to t equals 3. Well, x of t is just going to be a line that has a slope, and the slope is going to be dy over dt. It changes in height from 0 to 1, so dy will be 1, and it changes in time from 0 to 3, so dt is going to be 3, so the slope is going to be 1/3. And the equation for a line, y equals mx plus b, y-intercept is 0, so that b will go away. M is the slope, that's 1/3, and instead of x we have t. So x of t is 1/3 t. So a sub n will be 1 over big T, which was 3 seconds, times the integral between 0 and 3 of x of t, which is 1/3 t, times e to the negative j 2 pi n t over big T, which again was 3, all with respect to time. We can pull this 1/3 on the outside. It'll be 1/9 times the integral from 0 to 3. And now we just have t e to the negative j 2 pi n t over 3 dt. I'm going to do just a quick substitution. I'm just going to say a is going to be negative j times 2 pi n over 3. That way I can solve this integral a bit easier. It'll just be t e to the at, which we can use integration by parts to solve. I'll let u be t, so du will be dt, dv will be e to the at, so v will be 1 over a e to the at. It'll be uv minus the integral of v du. So it'll be t e to the at over a minus the integral of 1 over a e to the at. So it'll be t e to the at over a minus e to the at over a squared, with bounds between 0 and 3. And we said a was negative j 2 pi n over 3. Now we can just take that 1/9 that we had before, multiply it out front, and I can plug in these bounds. So it'll be 1/9 times 3e to the 3a over a minus e to the 3a over a squared minus 0 e to the 0a over a, so that will cancel out. We'll have minus e to the 0a over a squared, so the numerator is going to be 1. We'll have 1/9 times 3e to the 3a over a minus e to the 3a over a squared plus 1 over a squared. And a is negative j 2 pi n over 3. This can be simplified in a few ways. First, we can factor out an a. Next, we can see that e to the 3a will be e to the negative j times 2 times 3 times pi times n over 3. These 3's will cancel. We'll have e to the negative j times 2 pi n. And what this is saying is that for every integer n, which will be 1, 2, 3, continuing through all the harmonics, it'll be e to the negative j times 2 pi, which is equivalent to e to the 0, which will always be 1. So any e to the 3a is just going to be 1. So it'll be 1 over 9 times a times 3 minus 1 over a plus 1 over a. These two terms will cancel. We'll have 1 over 9a times 3, or 1 over 3a, where a was, again, negative j times 2 pi n over 3. So the reciprocal of this will be 3 over negative j times 2 pi n. So it'll be 1/3 times 3 over negative j times 2 pi n. These 3's will cancel. We can multiply the top and the bottom by j. On the bottom, we'll have j times j, which will be j squared, which is equal to negative 1. So it'll cancel with that negative sign. We'll have j over 2 pi n. So a sub n will be j over 2 pi n. Now there's one final thing we need to do, and that's to calculate the zeroth harmonic, also called the DC component, modeled by this equation, 1 over t times the integral of 1 period of x of t with respect to time. So it'll be 1/3 times the integral from 0 to 3 of x of t, which was 1/3 t. We can pull that 1/3 on the outside. It'll be 1/9 times the integral of t, which will be t squared over 2, bounded from 0 to 3. So it'll be 1/9 times 3 squared over 2 minus 0 squared over 2. So it'll be 9 over 2 times 1/9. These 9's will cancel, and a naught will be 1/2. So now that we have the zeroth harmonic, and we also have an equation to calculate the coefficients for any given harmonic number, we can verify that we have the correct equation by using Python. In Python, I've created a function that returns the coefficient value for any given number of harmonic using the equation found in the previous step. I loop through the first 100 harmonics, and I use the Fourier series equation to reconstruct the original signal, and I add the zeroth harmonic to account for the DC component of the signal. And as you can see, when I plot this, we get back the original sawtooth wave that we started with. So the equation found in the previous step and the zeroth harmonic are indeed correct. So thank you for watching.